so now that we've got a good handle on Z-scores and how to read the Z-score table, we want to use those skills to be able to solve some problems. So remember that we often get data that's not going to be exactly 1 or 2 or 3 standard deviations away from the mean, and so we're going to use those Z-scores now to kind of standardize the data and get some percentages here, right? So example 1, math test scores of Ramon's class are normally distributed. So again, we're being told that that's the case. So that means that we can use these Z-scores and the Z-score table, and we can use the standard normal distribution in order to solve the problem. The mean is 80. Okay, so X bar equals 80. And a standard deviation is 5, so sigma equals 5. Callie is in Ramon's class, and she scored 83 on the test. Compare her score with the rest of the class. All right, so, well, let's start by drawing a curve. Okay, that's not a lovely curve. It should be a little more symmetrical, but it's just rough. Okay, so 80 goes here, and then 1 standard deviation is 85. 2 would be 90, and 3 would be 95. Okay, and again, going backwards, minus 1 standard deviation is 75, 70, and then 65 is minus 3 standard deviations. And what we can see is Callie's score is 83. So we don't know exactly what her percent is, because we don't, right? We only know the exact percentages for anything that falls on these standard deviation lines. This is why we need to calculate a Z-score. So let's do that. Remember, Z equals X minus X bar over sigma. In this case, X is going to be Callie's score. Callie got 83. So that's her data point. The mean is 80, and sigma is 5. Now we already know that Callie did better than the mean, so she's going to have a positive Z-score. And she has, well, 3 over 5, which is 0.60. All right, so that's her Z-score, right? It's not quite 1 standard deviation above. So we need to go to our positive Z-score table that I've marked up, and we need to look for 0.60. That's right here. So her Z-score is 0.60. That's 0.7257. So that gives us 0.7257, which means that Callie did better. 72.57% of the class. Okay, because remember, everybody to the left of her is this percentage here. If we wanted to know how many people did better than her, right, we could say, well, let's see, get a good number here. So 100 minus 72.57, we could say 27.43% of the class did better than Callie, right? Because that would be this percentage here to the right of her score. Okay, so hopefully that makes sense. The second problem is a little bit trickier. It's only example 2. Got a little carried away here. Not example 3. It doesn't really matter. The mean lifespan of a non-stick frying pan is 2 years. That sounds like an X bar to me. And a standard deviation of 0.5 years. Carney is an avid cook and wants to replace her frying pan after 65% of its natural life. This is what some people think about, I guess. When should she replace the frying pan? All right, so we're given a percent here, right? So we're given a percent. So we need to turn that into a z-score. So we need to read, it's going to be higher, that's higher than 50%. So we need to use our positive table here, and we need to find a percentage that's close. So which numbers we've got? This guy and this guy. I think 0.6517 is closer to 0.65 than 0.6480, right? This is 17 away and this is 20 away. 20 thousandths, or yeah, 100,000. So don't worry about that. But this is as close to 65% as we get on our z-score table. Okay, so that gives us a z-score of 0.39. Okay, so that gives us a z-score equal to 0.39. Okay, so in this question we're given a percent and we need to work backwards to a z-score. So how do we do that? Well, what are we looking for? So we're looking for x. We don't know what x is in this question. We don't know when she should replace her frying pan. So let's use our z-score formula to see if we can figure out what x is this time. So let's substitute what we know. We know z is going to be 0.39. X is what we don't know, but we do know that the x bar is 2, and we know that sigma is 0.5. So we want to get that x by itself. So the first thing we're going to do is multiply both sides of the equation by 0.5 to get it out of the denominator here. So 0.39 times 0.5 is 0.195 equals x minus 2. So let's add 2. Right? So we add 2 to this side, add 2 to this side, so we're left with x all by itself. So x equals 2.195. What does that mean? Well, that's our data point that we were looking for. So Carney should replace her pan after 2.195 years. Okay, so a little bit higher than the mean, right? 65% is a little higher than 50%, so that number makes sense. All right, try the problems, okay? Ask if you have any questions.